Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
My aim is to sort of take you inside the computer and to explain how a computer is really put together, and then give you a sense of what are the scientific problems that require such huge computing capability, and some examples of the kind of things that large computations can do and what large computations cannot do. So let us begin by looking at a picture. Okay? This is a photograph of the Intel Gallatin processor. So if you open your laptop or desktop, and if you look for something like this, you're not going to see this. You know, this is the underside of the processor. So you can't even see the processor. You know, if you open the box, you can't even see the processor because it's inside a cooling system. But even if you remove the cooling system, you're not going to be able to see this because this is the underside and this is stuck to the motherboard. So what you're seeing in this picture are various pins. You know, there's a copper pins that are sticking out of the chip. Okay? So these are the pins through which information goes into the processor and information comes out of the processor. For example, you know, if you run a program or if you browse the web, you know, lots of signals are going into the processor through these pins, and a lot of signals are coming out of the processor through these pins. Right. So here is a diagram taken from one of the Intel manuals. You know, this is like a chart. You know, this is sort of like a map of what's happening with these pins. So there are coordinates. So one axis is numbered from A, B, C through A, N, and so on. And the other axis is numbered 1, 2, 3, and so on. So every pin has a certain coordinate and a certain function. For example, you know, if some data has to be sent in, if 64 bits of data have to be sent in, it goes in through maybe C43 and so on. You know. So every pin has a particular purpose. So the thing that I'm going to do in the talk today is, you know, we are going to sort of go inside the processor and see what is really happening. And then we will go outside the processor and see how it's all put together. So this is the Intel Xeon 5400 series processor, which is 3 or 4 years old. And a chip this size has 500 million transistors in it. Right? So there's just a huge amount of transistors inside this chip. And as you can see, the pin diagram is very complicated. There are lots of pins on this chip. You know, there are lots of ways information is going in, and lots of ways information is coming out of this chip. So 20 years ago, the pin diagrams used to be much, much simpler. You know, we had just pins on the sides, actually. So now, you know, there are pins over the entire surface. So 20 years ago, maybe there were 80 pins, and they would be arranged around the sides of the chip. Okay? So the first thing that we'll do is we'll go inside the chip a little bit, and we will look at the transistors and how they make computation possible. So the key to the computer is one of the marvels of modern physics, which is semiconductor diodes and semiconductor transistors. What is a semiconductor? A semiconductor can conduct electricity, but in a manner which is somewhat different from the way in which a conductor conducts electricity. Now, with the usual conductor, you know, metals, for example, are good conductors. If you decrease the temperature, you know, they conduct electricity better and better as you decrease the temperature. It's just the other way around with semiconductors. You know, if you decrease the temperature and you make temperature sufficiently small, you know, the semiconductors, they just become insulators. You know, they don't conduct at all. Semiconductors have another property that you can add some impurities to it. And if you add a certain kind of impurities to it, then the electricity is carried by electrons. These are n-type doped semiconductors. You can see it in the picture. One half of the diode is n-type. Right? The other half of the diode is p-type. So what is a p-type semiconductor? So it's a very good approximation to think of the charge carriers, the electricity carriers in a p-type semiconductors as being holes. So these are, you can think of the charge carriers as being positive and each charge carrier as having the same charge as an electron, but of the opposite kind. So you have to dope it with a different kind of impurity. So in a diode, you take a p-type semiconductor and an n-type semiconductor, and they're placed next to each other. Right? So this thing has some remarkable properties. And one of these remarkable properties is that diode is a rectifier. What does it mean to say that the diode is a rectifier? It's something which lets current go through in one direction, but doesn't let current go through in the other direction. So if you take a metal, for example, it conducts electricity, but it conducts electricity in both directions if you take a metal bar. But if you take a diode, p-type doped wafer next to an n-type doped thing, it's going to conduct in only one direction. Right? And here is the characteristic which shows us what that means. So this is how the current is a function of the voltage. And you see here from this picture that if the voltage is positive, then the current increases. Right? But if the voltage is negative, then there is no current. So there is a bit in the reverse direction, VZ, that's after the diode has really broken down. So you can really ignore it. But in the forward direction, as you increase the voltage, the current increases faster and faster. But in the reverse direction, there's hardly any current. There's actually a tiny amount of reverse current, but you can't see it in this picture. Right? So the important property of a diode is it lets current go through in one direction, but not in the other direction. Now, because it has that property, we can start building some logic using it. Right? And that is key because if you want a computer to work, then you have to be able to do some logical operations using the computer. For example, if you're adding numbers, you have to say if it's 2 and 3, it has to come out 5. If it's 3 and 4, it has to come out 7. So you have to start building logic in using your circuits. And using diode, you can build in some simple logic, such as the ability to compare voltages. For example, this is the circuit for a half-wave rectifier. It takes some math to work this out, but the math is not very complicated. But in this circuit, if you apply an alternating voltage at the input, at the output, the negative voltage is kind of set to 0. You can see two curves there. So the top one is oscillating. In the bottom one, see, there's only the top half of the oscillations are preserved. Okay? So that's because the diode is letting current go through in only one direction. So you can use circuits like this, and you can compare voltages. For example, if you put in one voltage at one point and other voltage at another point, you can make the circuit tell you which is higher and which is lower. Okay? So that is one of the operations that we need to do in order to build a computer. Okay. So here is a transistor. The physics of the transistor is similar to that of the diode. It's again, everything comes out of quantum mechanics. So here, you have P and P. So it's a more complicated arrangement. And below, we show the circuit symbol for a transistor. And there are two kinds of transistors that are shown here, PNP and NPN. So similarly, similar to the diode, the transistor is going to have some properties, but the input-output properties of the transistor are a little bit more complicated than that of the diode. The reason it's a little bit more complicated is because the transistor has 3 terminals, while the diode had just 2. So there are 3 points. So if you take the 3 terminals into account, there are 2 voltages and 2 currents. Right? So the relationship has got to be more complicated. In the case of the diode, there was just one voltage and one current. In the case of the transistor, there are going to be two voltages and two currents. So the transistor characteristic is a little bit harder to graph. But if you take two of the terminals of the transistor, a terminal which is called the base and the terminal which is called the emitter, and if you graph it, it looks very similar to that of a diode. However, if you take two other terminals, if you plot the collector current versus the collector voltage, then it looks a bit different. The only point that I want to make out of these pictures is the behavior of the transistor is captured by pictures like this. The currents and voltages, they have certain dependencies among each other. And if we do these graphs, then we capture the dependencies of the currents and voltages from each other. And the dependencies are a little bit complicated because there are two voltages and two currents that you need in order to describe what's happening inside the transistor. Now, using transistors, we can actually really start building in logic. For example, we can build the AND gate. The AND is one of the basic logical operations. If something is true and something is true, then it is true. For example, if I say red is a color, and yellow is a color, that's a true statement. Because it's true and true, then it's true. But if I say that red is a color and yellow is a person, that is false, because true and false is false. So one of the basic results of theory of computation is that you need to capture only a few basic operations. So if you capture a few basic operations, then the full power of computation can be captured. So if you want a completely powerful computer, you have to capture a few basic things, like and, or, not, and so on. And you need the ability to iterate and do conditionals and comparisons. If you have a few basic things like that, then you get the full power of computing. And the transistor allows us to implement the AND gate. And here's an implementation of the AND gate. There are a lot of circuit elements here that we're not going to describe. The point here is that every circuit element has a certain behavior, which can be captured by a mathematical equation or a graph. And if you put them all together, then the whole circuit is going to have a certain property. It takes certain math to work it out, how the outputs are going to depend upon the inputs. But if you work it out, and if you take the characteristics of the transistor into account, the resistor and the capacitors and so on, and you see how the output depends upon the input, the output is going to be an AND of the two inputs. Okay? So it may not appear like a big deal to you, like the AND is such a simple operation, but the whole computer is built out of very simple operations like that. Okay? By doing a lot of these simple operations and doing them in sequence and in a clever way, you can make the computer do many, many things. Okay? So the other thing that I want to mention is, I have told you a little bit about how to do operations using the transistors, but it's not just about doing operations like arithmetic and Boolean operations. You also need to be able to store data. So one of the basic elements for storing data is the flip-flop. And above here, you have the circuit diagram for a flip-flop. And the way this flip-flop works is, it's basically two circuits where the inputs and outputs are connected to each other, and it has two stable states. One of the stable states corresponds to 0, and the other stable state corresponds to 1. And by using a trigger, you can switch between 0 and 1. You can set the state of the flip-flop to 0, or you can set it to 1, and it's going to remain in that state as long as the voltages are maintained correctly. So again, this looks like a very simple circuit, and it just allows us to store a bit. But lots of circuits like this put together, they really make the computer fly. So So far, we have actually sort of looked at what a computer chip looks like, what its pins look like, and we have gone inside a little and seen what diodes and transistors can do, and got a little bit of sense of how the computer is built using diodes and transistors. Now, I'm actually going to go outside the chip, and for a moment, we are going to look at what a computer program is going to look like. Okay? So what you have up here is an example of a computer program. To some of you who have programmed computers, this might look very familiar. But even if you haven't, this is almost readable English. It can't get easier than this. X is equal to 1, y is equal to 2, z is equal to 3. And the three things are printed out. Okay? So this is a simple computer program. But this is not the form in which the program goes to the processor. So eventually, the program has to reach the processor, right? So I showed you those pins at the very beginning of the talk. So certain signals have to be sent through those pins, and the program has to go inside the processor, and the processor has to execute it. And this is not the form in which the processor gets this program. This is readable, and it's convenient for us, but it's highly inconvenient to the processor. So the form in which the processor sees the program is the following. Okay. To even some of you who have programmed quite a bit, this might seem unfamiliar. This is the assembly version of the program that I showed you earlier. Right? You really need to know the nuts and bolts of programming too. And you have to do a particular type of programming to ever see such a thing. There are very skilled programmers who have probably written hundreds of thousands of lines of code who have probably never seen an assembly program. Right? But the program that the computer actually sees is an assembly program. So this is the form in which the computer sees the program, but with one thing that I should mention. So every line in this program, for example, if you look at the text segment of the program, the first line is MOVL, $3 to %ECX. Okay? So that corresponds to a binary sequence, actually. So that is in human readable form. So we can actually read it ourselves. If you know a little bit about computers, it actually means something to you. But when it goes to the computer, that line gets translated into something in binary. And I'll show you a little bit of the translation in a moment, and it becomes a bit sequence. And that bit sequence is the one that the processor actually sees. Okay? So, every line in the text segment of this program, except the last line, which is a function call, it becomes a bit sequence. And it's the bit sequence that the computer really sees as the program. Okay? Not the human readable form that we saw earlier. Now, in this program, there were certain things like %ECX, %EDX, and so on. What are those things? Those are called registers. If you really want to understand a computer, you have to know what registers are. At least that's my opinion. You can write lots and lots of programs without knowing what a register is. But if you want to know how a computer really works, then the starting point has to be to know what registers are. And here's a picture of the registers of a modern x86 computer. So almost all the computers that we use today, I'm certain that 99% of the computers that we use today are x86 computers. And this is the kind of register set that the x86 computers have. So the registers are the places where the computer stores data internally. Instructions are going into the computer, data is going into the computer, and then data is coming out of the computer. So on the chip, the processor has to store certain information. Like suppose it has to add some numbers. It takes two numbers, it adds them, and it stores them in a certain place. Where does it store them? A lot of times it's in one of these registers. And when it does a lot of arithmetic operations, the immediate arguments to the arithmetic operations are going to come out of these registers. Okay? So in the previous program that I showed you, it said move $3 to %ECX. Okay? What that does is, the ECX register is towards the left, and it's third from the top. It's numbered, it's said RCX. It's titled RCX in this picture. ECX is the lower part of RCX. So 3 is going to go there. That's what that instruction is saying. So registers are the immediate targets for most operations that are performed with a computer. Okay, so there is a very fascinating story related to these instructions and registers. Suppose we take an instruction that says MOVL EAX to EBX. Okay? What does it mean? What it means is, if we go back up, EAX is the very top register on the left. EBX is the second from the top on the left. It's saying that take whatever is there in EAX and move it to EBX. Okay? It's a simple enough thing to do. So the code for that operation is 8903 in hexadecimal. So if you know hexadecimal numbers, you can easily convert it to binary. So this is a 2-byte instruction. It's going to convert to 16 bits. Okay? So this instruction corresponds to 16 bits, and that's 8903 in hexadecimal. Now the remarkable thing is this code 8903 for MOVL EAX EBX has been the same for more than 30 years. I think somebody decided upon this code for this instruction sometime in the mid-80s, I think. And even a computer today, an x86 computer today, which is most of the computers that we use, the code corresponds to exactly the same instruction. These codes haven't changed at all. Okay. So that's a feature of the x86 instruction line. So the x86 instruction line has something called backward compatibility. So every time a new generation of computers come along, they make sure that all the old instructions still run on the new computer. So that way, the old programs are not left away, are still able to execute on the new processors. Okay? So that introduces many peculiarities. There were instructions that were introduced in the early 80s, which would make absolutely no sense today. But they still have to be interpreted by the processor, and it still has to make sense of them because of this backward compatibility thing. So it has preserved its entire history beginning in the early 80s. Now, if we go back to this, and if we look at this, this thing here, some of the registers are called RAX, RBX, and so on. So it's a strange way to name things. That's again because of backward compatibility. They started out by naming them A, B, C, D because that's the natural way to name registers when you have just 2 or 3 or 4. And then there were many more, but then they had to keep the old registers because every new program, every new computer has to run all the old programs. So if you just look at the names of the registers here, there's a lot of history behind this. So as the computers have changed, the register sets have changed, but the old has to be preserved even as the design changes in order to run programs faster and enable more and more things. Some years ago, about 10 years ago, if you try to buy a computer, then people would tell you that, a 2 gigahertz computer is better than a 1 gigahertz computer, and it's twice as fast. It's absolute nonsense. It's no sense in it at all. But today they don't say it anymore because the gigahertz rating of computers has stopped increasing. The fastest gigahertz computer that you can get today is 3.3 or so. And if you go back 5 or 6 years ago, it was still 3.3 or so. So that number has not changed and probably will not change indefinitely. So how is it that the computers have got faster? One of the key answers to that puzzle, to that question, is instruction-level parallelism. And here is a slide which tells you a little bit of what instruction-level parallelism is. When you send instructions to your computer, suppose you send them in series. Do this, do A, then do B, then do C, do D, and so on. So there are a lot of instructions there, and it takes a lot of skill to make sense of what that's doing, but you can just treat them as instructions. It says do something, and then do something, and then do something, and then do something. But that is not what your computer does. Okay, what the computer does is, as soon as it sees this list of things to be done, it tries to automatically extract parallelism in the instruction stream. For example, the first 4 instructions there can be done in parallel, and it's almost certain that they will happen in parallel. Okay. So these instructions are being executed in parallel, even though it's a serial sequence of instructions. Now, without this idea, the computers today would be much, much slower than they are. Okay. So this became very big around 10, 15 years ago, instruction-level parallelism. There's a lot of technology that goes into making this possible, a lot of clever ideas that are used so that the computers can take a sequence of instructions, detect parallelism automatically, and execute instructions without dependencies in parallel. Okay. So now, I'll be going outside the processor. So before we go outside the processor, I'd like to tell you a little bit about the chipset. If you really want to understand how a computer is configured, the most important thing to understand is the chipset. Okay? So what is a chipset? The chipset is the thing which brings the computer together. And this is the chipset for, I think this is for the Xeon 5500 series computer. I thought it was in the slide, but it's not in the slide. So this is the chipset for the most modern series of Intel processors. At the very top, you can see 2 processor packages. The processor packages each have 6 processors on them. Okay. So there are a total of 12 processors in this arrangement. And then memory is connected directly to the processors. And then you can see that below the processors, there is a chip which is kind of, it's called Intel IOH. There are 2 Intel IOH chips. It's the north of the 2. Okay. And there's the PCI Express bus. The network gets connected to the PCI Express bus. So whenever you do things on the internet, it's going through that chip. The one on the top part of this, there's the equivalent of that on your computer. Your computers are going to be built with different chipsets. They're all built with different chipsets. The laptops use different chipsets than servers, and desktops use different chipsets and so on. But they will have the analog of this chip, and the network is going to be going through that. And below that, there's an other I/O handler. And this thing has lots of stuff connected to it. For example, your printer, your terminal, the disk, and so on, they're all connected to the processor through this chip. Right? So the chipset is the way the whole computer is brought together. Now we'll look at DRAM memory for a little bit. DRAM memory is used in all computers, and it's used on iPads and cell phones and so on. So the computer can't store too much on its chip. So memory has to be kept outside the computer. And the technology that's used to store is called DRAM. It's direct random access memory. But in computer science, the acronyms take on a name, life of their own. And it's, after a point, what the acronym stands for doesn't really mean so much. So the bits are arranged in rows and columns. And the way the DRAM memory functions is that the data is accessed row by row. So the most interesting thing about the DRAM memory from the point of view of organizing a computer is that the latency to DRAM memory is 100 to 300 cycles. What does it mean? If you do some arithmetic operation on a processor, it typically takes 1 cycle. For example, if you move data from one register to another register, it takes 1 cycles. If you take 2 registers and you add them together, it may take 4 cycles. Right? So it's all of the order of 1 or 2 cycles. On the other hand, if the processor wants to go and get something from the memory, or if it wants to write something to the memory, then the number of cycles it takes is a lot more. It takes 100 to 300 cycles. There's such a big range because DRAM memory is very complicated. It depends upon exactly where the word is in the DRAM memory and so on. It depends upon the order of reads and writes and stuff like that. But the latency is much, much larger than it takes for typical operations that just involve registers. So it's 100 cycles. It's about 100 cycles if the data is coming from near memory. Now, memory can be either near the processing core or far away from the processing core, as showed in this picture. So if it's coming from nearby, it would be 100 cycles. And if it's coming from far away, it would be around 300 cycles. This is a major problem in computer design because, so just think about a computer system which is very, very fast, but every time it has to go and get data from memory, it slows down by a factor of 100 to 300. Okay? Then your computer would be 100 to 300 times slower. Okay? So, and this gap is actually widening over time. About 25 or 30 years ago, the gap was probably just of the order of 20. I'm not certain of the numbers, but this thing has certainly been widening. So a lot of design goes into hiding this latency. And I'll tell you about the 2 basic ideas for hiding latency. I'm not sure if I can get rid of this. Would that be OK? The first major idea is instruction-level parallelism, which we've already seen. If the processor has to get 20 words from memory, it doesn't do it like this. Try to get one word once that's inside. Try and get the second word, and then get the third word, and then get the fourth word. That's not the way it does. It issues the request one after the other. It says get 1, get 2, get 3, get 4, get 5, get 6, like that. And then the requests are pipelined through memory, and then they come in back in some sequence. So there is parallelism in the way that the memory is accessed by the processor. That hides the latency to a very great extent. For example, if 10 memory operations can be in flight at the same time, the effective latency is reduced by a factor of 10. In fact, the number 10 is precisely true for modern Intel processors. The second major idea is cache. Okay? Cache is a very important idea, and without cache, all our computers would be many, many times slower than they are. And this is the diagram of an AMD processor, which is drawn to scale. And if you look at this diagram, you see that the processing part of this diagram is less than 50%. There's the 128-bit FPU at the top, which is used to do some arithmetic. And then there's load, store, execution, fetch, decode, branch. That's all used to do operations on the computer. So that's not taking up a lot of area. But on the other hand, there's L1 data cache, and then there's the L2 controller, L1 instruction cache, L2 cache. So that's all memory. Right? So that's nearly 50% of what's on your chip. Right? So the chip keeps a lot of data on itself because it takes such a long time to go and get data from DRAM. So it caches a lot of data on itself. So that way, the data that is most frequently used is always going to be on the chip, and it can be accessed very, very fast. Okay? So instruction-level parallelism and cache are the 2 major ideas for hiding latency. So there are very strange problems that come up when a lot of processors begin to access memory at the same time. For example, in this picture here, we have 8 processors, and there are 6 memory channels at the bottom. So the 8 processors can all use the 6 memory channels at the bottom. So they can send certain signals, and they can get data out of those memory channels, and they can write data into those memory channels. One of the problems that comes up is like this. Suppose customer A has $20,000, has a balance of $20,000. one of the processors might want to deposit $2,000 into A's account, and other processor might want to withdraw $4,000 from A's account. Okay? So if they both try to do this simultaneously, weird things can happen. For example, there's a word in memory that says $20,000. Both of them ask for that word, let us say simultaneously. Both of them get $20,000. And then one of the processors deposits and changes it to $22,000. The other processor changes it to $16,000. Okay? And then when they write back, the $16,000 processor writes first, and then the core which got the sum as $22,000 writes next and erases what was written by the first core. Then the balance becomes $22,000. Okay? So whenever memory is accessed concurrently by several processors, the processors have to coordinate. If they do not coordinate, they end up stepping on each other's toes. The way the coordination is done can be done in software. It's complicated to do it in software, but most of the time it's supported in hardware. So here, there's the sequence of instructions. The machine instructions are provided that enable the different processors to coordinate with each other. And that's just an example of the kind of machine instructions that the different processors can use to coordinate with each other. Okay? So we have looked at the processor and we have looked at memory. But if we want to get these gigantic computers, a single computer node maybe has 1 billion transistors on it, or maybe it's 1.5 billion transistors on it. But the really big computer systems of today have thousands of these computers, or tens of thousands of these computers connected with each other using a network. And we're all familiar with computer networks because we all use the internet, and it's a very big network. So now I'll explain to you a little bit of how the networks are put together and the kind of issues that come up in putting a network together. So this is a depiction of the internet. You can find it easily by doing a search. I'm not certain exactly what it means. It's visually very appealing, but what information it carries, I'm less certain. So here, I have a much simpler plot of a computer network. There are 3 computers, say ABC, and a copper wire that's connecting them. So if we just think about this simple picture a little bit carefully, we'll realize how complicated computer networking can get. Suppose A wants to send some signal to B. Okay? So A can use the copper wire and can send certain message to B. But the problem is B may not be listening. Right? So the computer B may be turned off, for example, or B may be doing some other activity, so B may not be listening. So it's not so simple. A can't just send a message and expect B to listen. So there has to be some coordination. Now suppose A and B coordinate, and A verifies that B is going to listen before sending the message, and then sends the message. But when A is sending the message to B, C may suddenly get interested in sending a message to A using the same copper wire. So you have to somehow make sure that C knows that it can't use that line because it's busy. So there are a lot of issues like this which come up in networking because it's a shared resource that a lot of computers have to use together. So one big issue that comes up in networking is flow control. What is flow control? See, when 2 people are trying to communicate over a computer network, it's very hard to determine what is the right pace at which to communicate. So A may start sending messages to B, and B may be a very slow computer. Right? So if B is a very slow computer, A will send a lot of stuff out to B, but B is not going to be able to process that stuff very fast. Okay? So if A doesn't slow down, then the network becomes congested because all the data just ends up on the network. Right? And if there's too much network congestion, then the network will fail. So what A has to do is A has to monitor the speed at which the receiver works. Now, if the receiver is too slow, then A has to slow down the speed at which messages are being sent. On the other hand, if the network is too congested, A again has to slow down the speed at which messages are being sent. Now, flow control is absolutely essential to any computer network. So without flow control, the computer networks would completely collapse. This is true for the internet, and this is true for the network, the kind of networks that are used to build large computer systems that are used for scientific computing. And for flow control, the receiver has to send acknowledgments back to the sender. Right? The sender has to monitor and make sure that the messages are not being sent too fast, and the receiver has to send acknowledgments back. Without this back and forth, the flow control is not going to be possible. Another big aspect of networks is error correction. Error correction can get very sophisticated mathematically. The point is that when you're sending data over a network, there are errors that come up. So the errors have to be detected, and if possible, the errors must be corrected. So there are usually error detection and correction mechanisms. Exactly how it is done, I'll not describe here, but I have written down certain polynomials. And these polynomials are used by a lot of networks which are in actual use in order to do error detection. The slide says error correction, but the codes that these polynomials correspond to are better described under error detection rather than error correction. Another very big idea in networks is packetization. Okay? This was a very big idea that came up in the mid-70s. This is kind of the start of the internet. So one of the great ideas about the internet was that it's a packetized network. What does it mean? So as we have seen, networks should have flow control. If there's no flow control, then there are going to be too many messages flooding in. There's going to be congestion. The network resources are not going to be well utilized, or they're going to be overutilized. And then we need error correction and so on. So to manage these things, it was realized that it's better to packetize messages. What it means is, suppose you want to send a message from A to B in the slide that is shown up here. Now, you might think that, suppose A is a server and B is your home computer, and you're watching a video. So the video is coming to you from A, and you're watching the video at B. So you might think that the video comes to you using a certain route. Now, that's not true at all, actually. So the video may be hundreds of megabytes, maybe even a gigabyte, over an hour of viewing or more. So the video is going to be broken up into a lot of small packets, actually. In fact, a single frame may be more than a single packet. And each packet is going to follow a different route. Okay? So the internet follows a packetized protocol. And the kind of networks that large computer systems are built on also follow a packetized protocol. Now, the packets follow different routes. Right? And a logical consequence of the packets following different routes is they're not guaranteed to allow in sequence. For example, the third frame of your video might arrive before the first frame. Right? So the receiver has to reorder the packets. This is a feature of all modern computer networks, packetization. An internet packet looks like that. That's a lot of stuff going on inside there that we're not going to get into. But let me point out a few things. If you look at the top left, third line from the top towards the left, it says time to live. Right? That is actually related to flow control. So this packet is going to be prepared on your computer. Suppose you send an email to somebody. It's going to travel as IP packets. Or suppose you get the New York Times web page. It's going to come through you as IP packets. So each IP packet is going to have a time to live on it. Right? That's for flow control, because suppose the network is very congested and your packet is just stuck at a router for too long. Then the router is just going to drop your packet, and the packet is going to be lost. Now, without a mechanism like that, the network wouldn't have any defense against congestion when too many people try to do too many things at the same time. And towards the right, at the same on the same line, it's the third line from the top towards the right. It says header checksum. That is for error correction. Now, it's using some kind of error detection and correction mechanism. So at every level of transmission in a network, you have to use some kind of errors detection scheme. And you can see this in the IP packet. So one of the things that happens in networks because of flow control, so flow control, error correction and detection, and then you have packetized protocol. And if you take them all together, one of the things that happens is you need to do a lot of buffering. Suppose you have some data on one computer. Suppose you have there's the New York Times webpage, and you click, and it has to come to you. So it doesn't come to you exactly in the format in which you receive it. The data gets changed into several different formats because the network has several different layers. And every time it changes format, it has to be buffered. Now, if you have some programming experience, you probably follow what I'm saying here better. And every time you have to buffer it, it creates some overhead. Right? So this is one of the ways in which networks can become a bit slow. Networks access is not as fast as accessing memory. There are several reasons for that. And one reason for it is any data that goes through memory goes through several layers. And at every layer, there has to be buffering done, and there are copying associated with buffering. And all this adds overhead, which makes the network slower, which are among the reasons which make the network slower than memory. Okay. The last thing I want to tell you about modern computer systems is the graphics processing unit. So we have sort of looked at what a computer processing chip looks like, and we have also looked at what the DRAM memory looks like. Now, the DRAM memory, I think some of you might have had direct experience of, because if your computer is low on memory, if you have a PC, you can actually buy memory and you can stick it into the box yourself. And some of you might have done it. But of course, you can never buy a processor and stick it into the box. It's way too complicated to do. And then we looked at the network and how it works. Now, if you have these computer boards and you connect them all using a network, then you get a really big computer which can do lots and lots of calculations at the same time. So in the past 5 years, there's a new sensation in this field, and this is the graphics processing unit. So if you go to Best Buy in Ann Arbor, you can buy a laptop. If you buy a high-end laptop, it's going to have a certain processor on it, and it will also have a graphics processor on it, which is for people who play video games. But if you run this graphics processor in the right way, it's going to be many times more powerful than the processor. It will be 4 or 5 times more powerful than your processor, which is quite amazing. Because the processor is supposed to be the center of the computer, and there is this little card. It's actually not a little card. It's much bigger than the processor in size. So there is this graphics card which has been put in for the video gamers so that they can play the video games and they go faster and they look better and so on. And it can actually do scientific problems 4 to 5 times faster than than the best processors can do. Right? And that trend has persisted for about 5 years now. So these things are called graphics processing units. So what is it that makes these graphics processing units faster than ordinary computers? And in what way are they not as good as ordinary processors? So the graphics processors actually have a much simpler design than the central processing units that we have looked at. So one of the things that I told you about the central processing units is, they have this instruction level backward compatibility. So an instruction that could have been executed by an x86 line computer back in the mid-80s, and almost all the computers that we have are x86 line computers, can still be executed today. From early 80s to today, the same instruction set can still be executed. But the graphics processors don't have that. They do backward compatibility in an entirely different way. The other big difference is the graphics processors don't have any cache on them. Right? So they use a lot of transistors, actually. So a single graphics processor card can have up to 2 billion transistors on it. So there's a ton of transistors in the graphics card, but very little cache memory. Almost all of it is used for processing. So the other big difference is the register file. So when we looked at the registers for the x86 type of computer, there were maybe less than 100 registers. But a modern graphics computer will have about 30,000 registers. Instead of having cache, they have a lot of different registers. But the bottom line is the entire design is set up in such a way there's lots and lots of parallelism in it. Right? So they don't have any cache memory, and they can do lots of stuff in parallel. In fact, if you're running a computer and a graphics processor, you have to make sure things go in parallel. Unless you put in a lot of parallelism into your computer, the program is going to be pretty slow. So if you do it all right, a certain set of scientific programs can be made 4 to 5 times faster, or maybe even 10 times faster on graphics processors than they can be on ordinary processors of the type that we looked at before. Right. So in the final part of my talk, I'll tell you a little bit about computer programs. I'll tell you a little bit about the kind of computer programs that can be written to solve scientific problems and give you a sense of where all this computing power goes. You might think that the computers are so big that we can solve almost anything on the computer. It's not true, unfortunately. There are lots of problems that we just can't do, and there's still quite a lot that we can do. So I want to give you a few brief examples of both. The first thing that I want to show you is something called the Navier-Stokes Equations. Some of you have probably seen it before, and if you haven't seen it before, it doesn't matter at all. The point is the entire set of equations can be written down in a single page. Right? It doesn't take more than a page to write down the full set of equations, but they describe a tremendous variety of phenomena. For example, the motion of fluids in microscopic ducts is described by this equation. And the atmosphere and the oceans can be described by this equation too. So there's a huge variety of phenomena that can be derived by this equation, by these equations. And the entire set of equations can be written down in a single page. What makes them so complicated to solve? The thing that makes them so complicated to solve is that even though the equations are really easy to write down, they have solutions which are really, really complicated when you look at them carefully. So here is data from an experiment. This is signals, which are recorded in an experiment. And this can be reproduced in a computation. And the time axis here is in milliseconds. Right? The x-axis is time, and it's in milliseconds. And if we reproduce it on a really big computer, milliseconds of computing would turn into seconds or even minutes of computing. It takes a lot of time to reproduce it. you can see the phenomenon is so complicated. The signals are changing in such a crazy way. The equations are so nice and simple to look at, but the solutions that are coming out of it are just so complicated. Right. So to be more concrete, it takes about 1 to 2, I would say about 10, I would say 1 to 10 billion grid points to fully, if you start with the basic equations of fluid mechanics, and you want to completely solve the basic equations of fluid mechanics without any approximations, it takes about 1 billion grid points for a 1 inch times 1 inch times 1 inch volume at the surface of a car at 60 miles per hour, right? And that is kind of the kind of computation which would stress the biggest computers, right? And 1 inch by 1 inch by 1 inch volume is just so tiny. Now, if you want to envelope the entire car, you can imagine how many grid points it's going to be. And the tires cause some peculiar problems because they shed vortices and so on. It's pretty hard to do the tires. And the physical phenomena that happen near the tires. So these equations have tremendously complicated solutions. And the kind of signals that I showed you in the previous slide, they all happen within millimeters of the surface of a car. So there's just a tremendous amount of stuff happening. And if you want to do it all, it just takes a huge amount of computing power. So the good news is that we can do quite a lot, but the other side of the story is that there's also quite a lot that we can't do. Okay? So in my last slide, I'll end with a summary of a computation which is related to quantum physics. So the computer is one of the marvels that's been made possible by quantum physics. So it's probably appropriate to end with a computation that is related to quantum physics. And I also have this little demonstration that the demo lab was kind enough to set up for us here. So this is some physics here. So when the temperature is sufficiently high, iron loses its magnetic properties. That's the Curie temperature of iron. So for example, here, this needle here, it's an iron needle, and there's a magnet on top, and you can see the needle is sticking to the magnet at room temperature. But now if I start heating it, when the temperature gets sufficiently high, it's no longer going to be it dropped off. Right? So it lost its magnetic properties at a certain point. So physicists can actually measure the temperature at which iron loses its magnetic properties, and it's 1050 Kelvin. Right? Now, there is a calculation from fundamental physics that was able to approximate that quantity. So you just have to know the atomic number of iron, which is the number of electrons in iron, and then some things about the electronic structure, from basic quantum physics and basic constants of physics, such as Planck's constant and Boltzmann constant and so on. There's a huge computation. It's ab initio physics with just 250 atoms of iron. Right? It's a very small number of atoms, but they came out with the value 980 Kelvin as an approximation to that. Right? And this computation used 100,000 processing cores, and it took 6 hours of computing to get that approximation. Right? So in the very last slide, let me just refer to some of the places from which I got the plots and the diagrams that I showed you. Some of them I made myself, but many I got from papers and manuals and books and so on. So thank you very much for your attention.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.